Well, let's get into replication. This is the last in a series of topics that we've been covering that have to do primarily with different ways or approaches of getting something more out of existing types of systems. So transactions was something that we used concepts that we learned already, and we built up this interesting mechanism of a transaction. There's some performance issues that we saw with transactions, and so that you can use something like replication to address those. But I want to address replication, first of all, in a more broad context, so we can see that it's a generally useful tool that has some consequences. And then I want to get into it a little bit deeper into how you can apply that to transactions or distributed transactions to increase the performance there. Now that gets a little bit more hairy, a little bit more complicated, but hey, that's what systems is about, is trying to make something that's very complicated a little bit simple, a little bit more simple. So what is replication? Well, it's a technique for increasing availability, fault tolerance, and sometimes performance. And replication can occur at many levels. You can replicate data, different copies of data. You can replicate computation. You can replicate communication. Something like have you guys heard of these tandem machines, these fault-tolerant machines? They're these big machines where you can take a sledgehammer to it and poke a knife through it, and supposedly just keeps running and running and running. Well, there's these machines that are used, for example, by banks or when you need systems that are extremely reliable. And these folks use replication all throughout this machine. They try to replicate everything, so there's no place where there's a single point of failure. And in that case, it's an example of when you use all three instead of just using one. Of course, when you start replicating, the natural consequence, and we've seen that this is actually a huge issue, is consistency. There's also coordination, which is a corollary issue. So once we start making copies, then we have to figure out, do we make them all seem like one all the time? And that's going to cost us. Or do we try to make it seem like allow a little inconsistency? And depending on where you are in that spectrum is going to depend on how you design that system and how the clients have to react to it. So here's some examples. The atomic writes via file logging. Remember we had replication of the data. So we had the existing copy, then we wrote the new copy. So we had this, and we put it on non-volatile storage. So by having these two different copies of the same thing, we could guarantee that we could either roll back or go forward depending on where we were. DNS versus grapevine, great example of different levels of where you want to set the trade-off, the consistency trade-off. And the scaling issues came out very nicely there. The RAID, here's an interesting case, because RAID, you do use replication for one of the reasons you want it in some of the RAID levels is purely for performance. So what's the trade-off there? The trade-off there is money, right? If you have these bit interleaved RAIDs, you can get a lot more bandwidth out. You might even be able to reduce the latency if you have the data replicated onto cache on the front end, but it's going to cost you a bundle. And then AFS, and if you remember in AFS, you cache the whole file so the data was replicated, and that's great because you get performance. You get better. You can have local reads and writes. You can have disconnected operation, which you'll read about in the CODA paper. But the problem there is that you can actually get into a really bad situation where the merge, when you come back in, is very inconsistent with a change that someone else made while you were disconnected or while you had your own version. So there's this versioning issue which we talked about. The reason it's not as big of an issue there is because people assume that this will be very infrequent. So these big problems are not going to have to be dealt with on any kind of a frequent basis. So let's think about how we can use replication for our transactions. Well, one of the things that we have to worry about is consistency, right? Because that was one of the reasons we're doing transactions to begin with, is because we want to make sure that all our states of any state that our system is in is going to be consistent. So that's why we need this atomicity, we need the recoverability, and all of that. So now we're actually pushing things to the limit of how do we get that consistency and to be assured, and what are the trade-offs we're going to have to make? How do we get around them? Well, the thing that you're aiming for is one copy semantics. So the semantics there is that when you access an object, it feels like that there's one copy of it from the transaction point of view. So the transaction isn't going to know that there's multiple copies sitting around. And that if you do that, then what does that mean for your existing transaction code when you start replicating objects? Backwards compatibility. That's always a good goal, because if you rewrite the way the semantics for how you access objects, now all of a sudden your transactions all have to be changed to take that into account if they can see that. So the one copy semantics assures some kind of backwards compatibility with your existing code. And again, the big problem is if we had perfect conditions, if we had completely reliable networks, completely reliable servers, this might not be, replication for transactions might not be as big of an issue. But unfortunately, we have to deal with these two issues. That's where the hairiness comes in. Questions so far? Okay. So I usually like to start by giving a simple model so that we can, sort of the most intuitive thing you might synthesize, and then start addressing some of the issues that come up in that. So imagine that what we did is, to do this, we had a set of replicas for a given object. What we did is that what's called read one, write all. So if you want to read, you can read from any one of these. And so wherever you are in the network, you can say, great, I'm closer to over here. I can just go locally and everything. You get these reads faster. Oh, that's cool, because that's one of the reasons you replicated. Now, when you write, well, what do you want to do? If you send a write to this one, you want it to propagate over to all of them, right? Because then that way, everyone will have a current copy. Now, in order to do that, what's the issue that you have to get around to make sure that you don't get an inconsistency here?
You have to make sure that all of the places where you're writing actually get the information and make a change.
Okay, so one is that they actually get the change, and what's the other one?
That no one else can write to one while you're writing to another.
Right, so you can't have this one writing to this and this one writing to this, and then those colliding somewhere, because then your transactions will fall apart. So what's the technique that we learn to get around that issue? Locking or mutual exclusion, right? So if you're doing a write, one straightforward way is to use what we learned how to do, mutual exclusion or locking, and just go through, lock all these guys up. If you can lock them all, then you can write to them, and then once everyone's updated, then you say, okay, now everyone can access the system again.
If someone wanted to read while the write had not been committed throughout the system, you may want to notify them that they have read something which has proved to be out of date.
So if you want to do a read if you're going to be doing, it depends on the type of lock that you're doing. If you're reading something that's not going to impact, and not going to do a write, that's not going to impact something, it's not going to come back and impact someone else reading, then you might want to just have a read lock on it. I'm sorry, a read only lock on it. You might want to have a read-write lock on it also if you think that if you don't want anyone else to access it while the system is running. So it depends on what type of transaction you want, but you're getting at the issue that I think you're getting at is, if you have these different types of locking schemes, and if you have to go out and grab locks on everything to do the kinds of things that we've seen you sometimes need to do, then you get into performance issues. Right, so what happens when one of these goes down and you're trying to do an update? Well, it has to be available, right? Because if this goes down, you do the update to everything that's here, and then you come back, this one can have the old version. So now we have a consistency issue if something goes down. We have to solve that issue. The other thing is, the worst issue is actually what happens if the network gets partitioned? What do we do in that case? What do these guys do? Do they all just kind of wait around and sit around, or do we allow things to be updated, and how are they merged? So these are the two kinds of issues that we have to solve, and we can do that. There's approaches that you can do to solve these, and we're going to go through a few of them. thing to keep in mind as you go through them is pay very careful attention and try to understand what the assumptions are behind and what the trade-offs are. Because when you design systems that use replication, what you need to do is match these different techniques with what you think the underlying assumptions or system characteristics are going to be. So let's take this network partition a little bit deeper. It's a huge issue because you can have links go down. Right, links can go down because of congestion. Congestion can happen at unpredictable times, and when something gets congested, even if a link is down, say for a few seconds, that could stall. If you're running hundreds of transactions per second on this, or you're trying to, that could stall the pipeline of transactions, in a significant way. That's the more serious of the two issues, the server crash versus the network partition, in part because servers have become more reliable these days. So it's the network partition the network hasn't become, in a sense, more reliable and less congested. It's going the other way instead. So there's a couple of options, there's a variety of options, but they generally fall into two categories. One is called an optimistic strategy and one is called a pessimistic strategy. And you decide between them based on how much contention there's going to be for resources and also what your model is of how often these network partitions are going to occur and how long they're going to last. You'll see that why as we start getting into them. So in the optimistic approach, the reason it's called optimistic is because you're going to assume that what you're doing, that you can go ahead when network partitions occur, you're going to assume that you can go ahead and try to do as much work as you can, and the optimism is that you're going to be when you get connected, it's going to be something you're going to get connected more quickly, but you're also any inconsistencies that arise are going to be minimal. So AFS is an example that uses an optimistic strategy. They're optimistic that when you make a change to a file that's local, that's not going to cause 50 people out there all of a sudden to have to do a lot of work. So they go ahead and say, well, if you write the file, then I'm going to say I'm going to just write it out and let the merges be dealt with later. What's another system that you guys have used that has optimistic? CVS. Right, CVS is very optimistic. It says, well, if someone else has a copy of this thing and then you do the merge later on, if there's some really bad thing, it tries to merge intelligently, but if it can't understand how to do it, then a programmer has to deal with it. In the worst case, two people just wasted a week of their time. So in the optimistic approach for network partition, what you have is you say so this is a general approach. Any of these replicas can act on behalf of the whole. And as partitions, as the partitions come, so if you have a partition, then this one here can act as a replica for a set of servers that are doing transactions on this object and the same over here. When the network partition dissolves, so you get connectivity again, then what you do is you attempt a merge. So you take whatever objects were over here and whatever objects are over here, and you try to merge them. Now, if different objects were modified here as were modified here, do you have any issues? Hopefully not. I mean, they're different, so you just take what was modified here, write it over here, take what was modified here, write it over there, and you're done. So that's case number one. Case number two, there's a merge, but it's something that you can solve, where you can actually use a machine algorithm to do the merge itself. What's an example of that where the machine can actually decide one thing or the other in a system that you've seen before?
If you have timestamps and the latest timestamp,
Right. So there's timestamping. If you have a timestamp and you just use that as the order, the latest timestamp is always the one that, then you can use that as a way to merge. Imagine in something like DNS, you could always have a decision that if you get two inconsistent updates, you might say, well, I want to make the system consistent, so I'm going to pick one. Right. That's something that you could do as a fallback. Yes.
When we did mutual exclusion, we looked at Lamport clocks because you couldn't have accurate timestamping across a distributed network.
Right.
Is that just not considered an issue here?
With timestamps?
Yeah.
Well, the land port clocks allowed you, they imposed a total ordering because if the times, you use both a timestamp plus a process ID. So as long as the processes were totally ordered, then in essence the process ID gives you a coarse-grained ordering, and the timestamps can give you a more fine-grained ordering. And depending on the inaccuracy of the clocks, you might have some situations where some things where you do have skew, but you can still do an ordering.
When you say merge, the timestamp thing to me isn't what I understand by merge, where you're not making any attempt necessarily to combine the contents of the two files. You simply got a decider for which is the valid and which is the invalid current version.
Right.
And you just write over the invalid one.
Right. Well, it is a form of merging in the sense that in one case, a merge can be, like, say you're trying to merge, say someone blew away a file and someone kept it around. That merge would be, well, let's keep the file around just in case, if it's source code. So it's a more absolute form of a merge. When it gets tricky is the third case, which is what happens when the merge requires something that a machine can't figure out without being AI complete. And so the example of that is something like code. Over here someone grabs a source file, over here someone grabs a source file. I mean, that's the best example. They both modify them all week, and then they come back and they're like, okay, let's put them together, and they look completely different. Computer, because it can't, number one, it can't solve the halting problem, and number two, it has no idea what the intent of this program is. It's going to have a very hard time merging those two pieces of code together. Another example of that, which we've seen, is the bank account example, right? If we have two different bank balances at the end of this, which one do you pick? I know which ones I would want to pick, but if I were the bank, I'd want to pick the opposite. So the merge there can be more complicated. If you have access to a transaction log, you might be able to sort it all out. But if you don't, and banks might not want to share those transaction logs with each other, then you can get into a more difficult situation. So what's an alternative approach? Well, you don't have to necessarily give up in this case. For example, one thing that you could do is you could say, well, if I'm cut in half and there's an inconsistency, then what I do is I'm going to just not commit until we get the connection back, and then one of us will abort. If two writes are being made to one object. But there's alternative approaches, which is you can actually try to manage the inconsistencies outside of the transaction mechanism. A great example, which we've been talking about before, are ATMs. Remember how these ATMs in California, where they would say, well, if I'm partitioned and I can't talk to I can't get the bank account balance, then I'm just going to go ahead and give the money away and commit there. The problem being that you can have an overdraft situation. But these banks realize that, well, you can manage that to a large degree outside of the transaction system. So even though there was an inconsistency, which was one of the parameters could be the bank balance will never go below 0, right? You can imagine there being some way of adjusting that once you get connected and setting up a flag for someone to come back and suck money out of you. Some of you, I mean, these banks will send letters sometimes and say you need to put money immediately. If you have a line of credit, they might just suck money out of that. You might get a phone call. You might get someone knocking on your door eventually, depending on the amount. Fortunately for the banks, those types of situations were very easy to handle. So instead of trying to make this system more complicated and trying to make sure that certain types of consistency guarantees that they wanted were met, they figured that it's cheaper to do it outside the box.
That's a situation though where you can actually merge objects themselves, right? Like they don't pick one of those objects, one where the $10 withdrawal was made and one where a $5 withdrawal was made. They actually can sum them together when the partition goes away.
Yeah, but in that case, you still have the case that there was some condition, some consistency condition that you didn't want violated, which was overdraft of an account.
You can, like, that's sort of a special case, like, right?
That's one case. There's the datebook case also, which is a little bit is a different flavor of it. The datebook case. Suppose that you get a partition and you're trying to set up a meeting. This is, I think, probably will feel better for you from that angle. You set up a meeting, and suppose there's a network partition. And you say, well, I can read from over here, and I know that you, and you, according to this replica, are free at 1 a.m. on Friday. And so I'm going to go ahead and just commit that. And then when the network comes back up, you go over there and you try to replicate that to everybody else. Now, if someone else reserved that time over here, then there's a merge condition that needs to occur, right? So which one do you pick? Well, if you the machine could just pick one, but you might not be too happy with it. So what could happen in that case is you get some message saying there is a conflict and you have to decide. Or you could go back and the system could say, well, now the way I'm going to resolve the conflict is to try to reschedule this and then send out you new messages and figure out what times actually are available. So in that case, the way you fix it is by either running another transaction or asking people to change to decide between what they want and what they don't want. Does that make sense? Thing to take away from this optimistic is you try to optimistically assume that these merges are going to be handled, or when they can't be handled, that there's either some way outside to do it, or that the expense of doing it is going to be small, amortized to the performance gain that you get. So a more detailed example of this is what's called available copies replication. So in this approach, same kind of setup over here, you have replicas. And you have machines doing transactions. And you start off by assuming that any available replica manager can process can act as a proxy for the object that you're dealing with. There's some object that these guys might all be dealing with. There might be another set of ones over here that are dealing with, that have some other object. You can have situations where these guys are all responsible for some object. That depends on how you want to lay things out. So the way this works is reads are fine. You can go to one replica and say, I want to read this value. And it'll say, great, here it is. And if you want to write this value, the replica is responsible that you're dealing with is responsible for making sure that that gets propagated out to the rest of the replicas. Now you have, as we talked about before, you have some locking that you can do. So if you come in here and you say, I want a read-write lock on this because I'm going to read the value and then I'm going to add an amount to it and I'm going to change it, this guy will say, great. Now the interesting thing about this algorithm is at this point, this replica doesn't propagate that lock out to anybody else. This is a performance saving step. So it locally just says, okay, the lock's there. So what issue do we have to consider now if that's the case?
Someone else might do it on another.
Yeah. So someone else might be over here and say, oh, I want that same type of lock over here. And this one will say, sure, and give that until you have a lock on it now. So the question is, there's transactions running here, and there's different, now we're in a weird situation, right? There's different transactions with locks on replicas of the same object, but we have to maintain this one object semantics. So how can we get around that? Any ideas? What's that?
Two-phase.
Excellent. So how would that work?
Each of them asks all the others in the network if it's okay to lock and then overwrite the others. And if one of them says no, then we have some kind of backup procedure.
Exactly. Exactly. So this is interesting because now we have, in essence, two levels of two-phase commit. We can have a bunch of transactions that are running up here, who are going off, grabbing objects and running just like they normally, like we saw the last couple days. But then when they actually when these guys want to commit, they'll go and tell for each object that they have a lock on that they're updating. They'll go tell its corresponding replica commit. So now there has to be a two-phase commit protocol down here to ensure atomicity in that update. So this guy's going to go around and ask everyone, I want to update this object. Vote yes, or vote like a two-phase commit. Vote yes or no. What's this guy going to say if he gets something like that? He has two options, right? If he says, if he says no.
You can say no, in which case they'll have to abort, or he can say yes and abort his own process.
Good. So he can say no. If he says no, then this guy wins and his thing proceeds. If he says this, if this guy says no, then this guy has to abort. If this guy says yes, then at some point this transaction over here can be aborted, right? Because that's the whole idea of the transaction, is you can recover from it and roll it back. But think about the performance cost of this. Where are we getting really nailed? Well, we have two-phase commits, and so there's all these messages running around, and that's going to limit the amount of transactions we can handle per second. So this is why this is an optimistic strategy, is that if we have a lot of situations where the same resource here there's a lot of contention for that same object, and lots of people are trying to write it, guess what? There's going to be a lot of aborts happening. And that's bad, because the whole reason you replicate it is because you want to improve the availability and performance here. However, if it's the case that these updates are going to happen relatively mutually exclusively just by the nature of the application, then this kind of system will ensure the consistency, will give you better performance, because locally you can go and access only one replica, and then you take the hit only at the end, but you don't have to worry so much about aborting all the time because everyone else wants that same object. Does this make sense so far? That there's two levels of this, that we're using two-phase commit at two different layers in this architecture. And we're using them both for the same reason, which is that we want to make sure that a set of objects or a set of things are atomized. In this case, it's the writes to the replicas. Yes?
Why do we gain performance by doing the check after the work has been done rather than before?
After the work has been done.
You're saying that they don't check until it's time to commit, whereas they could ask each of the replica managers before going in and getting the lock.
Okay.
And it seems like you still have to check either before or after.
Yeah.
And that check is going to be the same bandwidth to communicate.
Right. So, yeah.
Nodes.
So let's come up with some situations where it would be horrible to ask up front versus later on. So one of them is, imagine that your network is not that reliable, and that so what happens is this becomes a blocking operation right up front. So right up front you're doing reads, and you have to wait for everything before you can do any type of crunching. And if you wait till the end, then after you've done all the crunching and you're waiting to commit, then that's at the point where you take the hit. Now what that means is that if you're doing a transaction, and so let's augment that situation. You're doing a transaction. Suppose that your transactions, because you have a more unreliable network, tend to be your abort rate tends to be a little bit higher than you'd like. Well, if your abort rate is higher, then you'll never have to go and do this two-phase commit down here on this object if you abort the transaction before you get to the commit. So in that case, doing that work up front doesn't get you anything either, because you're doing a lot of work up front, and if you think there's a reasonable chance of aborting, then that work is wasted. So what you can actually, you can imagine you can model this with a pretty simple set of equations, just like we modeled the whole process, the virtual memory on the quiz. Those parameters, like the network unreliability, the frequency, how often you're going to be accessing these, the frequency of aborts, you can put all those variables in an equation to help you compute the number that you want, which is it better for me to do this ahead of time or not or later? And you'll get you'll get an answer out. You try it and then run some experiments to see if the model corresponds to what your assumptions were.
But you'll get a dynamically changing answer, but you won't have written code to be able to adapt.
Well, that's the thing, is that when you see your answer, you can try it one way, you can try it the other. If the model is all over the place, then then you have to try some different approach, like maybe a probabilistic approach that adjusts for the time of day when there might be more congestion or less congestion, or more aborts or less aborts. And if it's important to you, then you can try to push it to that level. Now, one thing that and when you read the assignment, the book tonight, that you should pay attention to is this. One of the assumptions here in the algorithm I presented is that server failures can be detected. Because imagine that you're going to this replica here and you're accessing it. This one's coming over here and accessing this one. And then they've both got some kind of locks on them. But then this one goes down. And so this one can say, oh, I'm going to do an update. Well, let me look at who's at all my available servers. Oh, OK, boom. Here, I'm going to go ahead. They all say yes. Now, one of the reasons you wouldn't want to wait for everyone to come up is because you don't know if they're going to come up, and then, or when they're going to come up, if they're going to come up. So you would that would be a bottleneck. So one of the ways that you approach that, there's an algorithm they show in the book, it's called validation, in which if you can actually detect these failures, then you can order transactions and decide whether one of these gets precedence over the other. So like we did with timestamps, there's a way of ordering using a logic to induce which one gets priority based on when you observed the failures of the replicas. Yes.
So we took away the network partition in this example. Is that right? Like
Well,
if this gets partitioned, they can't ask each other permission for a lock. So does that mean that they always fail to get it, or does that mean they always get it?
You get the lock locally. So you can always, as long as you're communicating with one replica, you can get that lock locally. It's when the two-phase commit happens that you can have that's when you have to propagate that and do the atomicity. So if you get a network partition, then you can address it using some of the ways we talked about before.
Okay, where you either just do
You
optimistically charge.
Yeah, or you can abort if you want, or if you're in a nested transaction and you abort, then this guy might go off and try some other way. But that you'll get what this is trying to do. This approach here is it's trying to mitigate the cost of these potential network failures, because you're dealing with somebody local. And if that someone local is on your same subnet, then you can carry out a lot of you can increase the performance dramatically and then take a hit, at the end when you're actually ready and you're done with everything. Now, another instance where it might be better to take the hit later on is, imagine if you're in a nested transaction system and you're coming in here and you're trying to grab locks, grab a bunch of locks that are all going to be in the same, that are replicated all in the same set of servers, right? Then you can, at the end of this whole thing, then only the locks, then you can still use one two-phase commit to update all of those objects at the very end, and you only need to update the ones that you end up using, because if you have some nested ones that abort, then you don't have to deal with those at that point. Okay. So, following up on the question about network partitions, the opposite situation is a pessimistic one. The pessimistic one is that you assume that merging is something really bad. It's either really bad, it's going to happen enough that you don't want to deal with it, and you want to figure out some way that you can still have that replication can still give you some benefit, but you don't want to pay the price of the merges. So what you do there is there's one approach called a quorum approach, and what it says is that if there's a network partition along the way, that what the partition is going to induce is subsets of this network, and one subset of that network can act as a proxy for the whole network of these replicas, and that subset is called the quorum. To get a quorum, you have to have, so let me write this out here. If you're the number of people for a read quorum, or for a write quorum actually, has to be greater than half the total replicas. Okay. Now, the number that you need for a read quorum has to be greater than the total number of replicas minus the number, this W number. Okay, now let me put a little more intuition behind this as to why this is important. So what you want it to be the case, the goal of these equations are it to be the case that when you make an update to something and you have a write quorum, that anybody else, that any other read quorum that you have will be able to detect that write at some point. So there's one other assumption we have to make for that, is that we can use some kind of timestamps, some kind of mechanism, which could be timestamps, to give us some total ordering. So imagine that we had a set of replicas. What this equation up here says, the W1, is that to get a quorum, you have to have sort of half plus 1 at a minimum. So that means that you can't ever write to a replica unless you've got half plus 1 at the minimum of all of the replicas willing to be able to commit that write. Now, what R says is that in order to be able to read a value and successfully know that that's the current value, that you have to have at least, so the total number of replicas, which is this, minus W, so you have to have at least one more than that. So you have to have at least, this is, this many in your quorum.
How is that the total number minus W?
It's got to be strictly greater than. So these equations are set up so that if I suppose that I had a write quorum over here, and I wrote this new value out. These equations are set up so that I can take any other read quorum in here, and there at least one of those replicas is going to have the latest version of my object, which in this case, and the way you can tell whether it's the latest version is by your total ordering. So the way you read a value is you go to the members of your read quorum and you ask them all, what's the value? And then when you get back, you order them according to this total ordering, and then you take whatever one was the most recent update, or however you do that ordering, and that's the one that's the value you're going to use. So you notice that it's okay in this case if the updates haven't made it all the way across to everybody. So we actually get some amount of performance out of that, because now our requirement isn't that everybody has to be updated. It's that at least more than half have to be updated. So no matter how we choose this pink region, we're always going to have at least one member of the one replica that's going to have the most recent value. Yes?
I can see that would work if you had a write and then a read, but what if you had a write and then a write?
So if you had a write and then a write,
yeah.
So let's say you had two writes. So let's say you had this as your first quorum, and you wrote to all of those. And then say you had this over here as your second one, and you wrote to all of those. Well, what's going to happen is that these over here are going to have of all of these here. These here, actually all of these here are going to have the most recent value. These are going to have the older one of the older version. But when you take a read quorum of these, any read quorum that you take is going to include at least one member of this most recent write.
Why are you saying when you take a read quorum?
A read, so the algorithm to read is you have to get a quorum of replicas to be able to read.
But I thought we just had two writes, so how does the read come in?
So if you do a read after the two writes, yeah, if you do the read after it, if you do it in the middle of it, is that what you're asking? If you
No,
do, okay.
But then how do you ensure that you hit a different subgroup? Because you wrote.
Yeah, you don't. The way that you ensure it is because to get a read quorum, you have to have at least the number of replicas that you have to read from has to be greater than the total number minus W, which will always include at least one member.
But what about the two W's in a row? How do you ensure you get two different subsets? I thought your explanation just relied on.
You don't have to have two different subsets. To write, you just have to have one more than half of the number of replicas. If it's an even number, if it's an odd number, then you round up to the. So you always have to have to write, no matter which set of these you pick, it has the number of those replicas that you write to has to satisfy this condition.
Okay. Then I was confused because when you drew it, you drew two different subsets for the writing. You just duplicated.
I was using this as the worst case scenario. So like the worst case, like what's the worst case scenario is that your reads can't be seen by your writes can't be seen by a read. Right? So if we try to come up with something where you have a quorum, and I mean that's what you want to get around is that when you write to a quorum, it has to be the case that when you create a read quorum, that at least one member of that read quorum will have the most current value of the whole system. Okay. And we're trying to do that by using this condition here combined with this one, using an ordering. Is that?
I sort of see that. I see
okay.
It like you find the inconsistency.
Mm-hmm.
I'm not sure I see it when you do two writes in a row. Where are you going to find the inconsistency?
Oh, well, when you do two writes in a row, there's going to, at the end of the second write, there's going to be at least more than half of the replicas are going to have the most current value. And so the idea is they keep propagating. I mean, the idea is to keep propagating those values out, but you can't assume, because of network partitions, you can't assume that you're going to be able to do it anytime soon. So you write to one of these, and then you do your best, but at some point in time, the worst case is you can't get it out, and someone else wants to read it right afterwards. So the guarantee you have to give the reader is that if they have at least this many, that they'll have at least one member who does have the most recent.
So if there's a partition that persists through your writing and your reading in one place, then you're going to get your write quorum on the bigger side. If it's right down the middle, then you can't do either.
Well,
you could never write.
That's right.
If it's off to one side, then you can write over here in the big half.
Right.
Half,
yeah.
And you can read over here too.
Right.
And anything that's trying to read from over here is going to be locked out until the partition goes away. Right?
Until one member comes over.
But that's if it's.
See, that's the interesting piece, is that in the case that you just said, all you need is one member of this write partition to be available to the other side, and all of a sudden those guys can start reading. So that's why you get that's where the interesting dynamics come in for performance, is that instead of relying on everyone being able to come over, all you need is one. Yes, in that case.
So for example, if your first write changes a variable like A, and your second write changes a variable B, and you go into read, it might get the new values for those two different variables from two different places?
Yes. Yes, okay. That's right.
So you don't need to be in that little quadrant where it has both. Like you don't need to be able to see one location that has both the new A and the new B, because you can take them from
different. Yeah, that's right. This is on a per object basis. So it may be that some objects have more replicas than others, but and they can be very different replicas. And that's right.
Does this now mean reads have to become massively more bandwidth consuming because you have to read from all of these?
You have to be able to. Yeah, that's right. That's right. That's absolutely right. So one of the ways you actually, it's a great lead-in guy here. So one of the ways that you address that is you actually can put weights on these different machines, and the way that you assign these weights has to do with, for example, how close they are to you, what kinds of reliability characteristics you have. And there's a paper that came out of Xerox PARC by Dave Gifford when he was there. Dave is now a professor at MIT, where he goes through and gives proofs for how the weighting system will work. Dave Gifford was actually at PARC when all this stuff was going on, like the grapevine and sort of the heyday. So if you ever get a chance to talk to him about that, I'm sure you get some interesting stories. Okay, so this is pessimistic because, again, just going back to optimistic versus pessimistic. This is pessimistic because if you have to be in some kind of state where you can guarantee consistency, and if like we said was mentioned over here, if you don't have a read quorum, then you're stopped, you're blocked. You're not going anywhere. So you can imagine there's a variety of these types of algorithms. Another one which you can read about in the book is combining these two into what's called the virtual partition algorithm. Now, what you do there is you use the locality. This algorithm, this one over here, this optimistic one, you can, in a local subsystem that these conditions, the assumptions here are better satisfied, whereas more in a more distributed way, these are satisfied. You can combine both of them and, in essence, create virtual partitions. So you can say a transaction is going to act in a artificially created virtual transition that actually has quorums in it. Now this is going to work if you can use weights for the different servers, so that you can actually go and work with a subset of these. You don't have to go out there and read all these different ones that have one vote. Now some of them can have 10 votes, some of them, so they have this weighted algorithm. And if you combine those two approaches, then you can get the benefits of the pessimistic consistency guarantees combined with sort of the optimistic performance gains. All right, so putting it all together, you guys have learned a lot of different ways of, a lot of different techniques. You've learned about transactions and locks and replication. So how does this all fit together in a system? Well, transactions, you remember, we got transactions by being able to implement atomicity and recoverability, or being able to roll back. Okay, those are the two main things. If you have those, great. Can implement transactions. And in fact, you could, using what you've learned, I think it would be pretty straightforward for most of you to go actually and implement a transaction system in Scheme or in Java that would have real safety guarantees. The reason you can do that is because you can get, for example, atomicity using locks, and you know how to do locks because there's different ways you've learned how to do mutual exclusion. In fact, if you want to really push it, you can try these consensus type algorithms, but that's something that we've learned how to do. We can do atomic rights, which help with recoverability, using logging, like we talked about before on the board, about how you can make sure that rights, especially longer ones, either are all or nothing. So you can actually, once you implement that, then the question becomes, well, how do you push the performance envelope on it? And so we've learned of a couple ways to do it. Distribution is one, and replication is another. So you can distribute transactions, you can do nested transactions, and we talked about the semantics there. And then replication is what we talked about today, is how do you replicate the data around so that you can have better access to it. The bottom piece there, this first part here, I'm pretty sure you guys could just implement a pretty generic, pretty basic, safe transaction system within a day. No problem with what you've learned. Whenever you're doing this in real life, it's the piece down here, the performance and availability, that nails you each time. I had a friend who worked at Oracle, and he said that these guys get down to the nitty-gritty assembly language level to code some of the bottlenecks and to deal with some of the performance issues. Because that's the best way to deal with them, which is really nasty because you don't have all these nice abstractions to be on top of, but that's what ends up working for them. If you want to start doing distribution, like anyone who gives you distribution, is really hard. When someone gives you a transaction system and says this is the fancy distributed transaction system, what you've learned is that what are some of the issues in distribution where there's all this about consistency, about failure control. That's how you would go and critically analyze a transaction system. One angle. The other one is replication, optimistic, pessimistic. What does that imply about the performance? You've also learned that when you're thinking about the performance, as soon as you put the network in for the transaction system, that tends to become one of the key bottlenecks. So you have to start thinking about round trip times and how that's going to affect things. That's one of the hints of where you should look to first. And the bottom line here is that the implementations can come in many flavors. One of the approaches that I recommend is what we talked about up here, is just if you don't know which approach to use, come up with a model It can be a simple model like we did on the test to figure and write down what the key parameters are that characterize your model, and then figure out what the rate of what's the bottleneck in that of how many transactions per second you're going to be able to do, given your assumptions. And that's going to help you differentiate between the different models. So with that, are you guys going to all implement this stuff? You can. I have no doubt that each of you can do it. If you've written this Nutella client, I'm sure each of you can do it. Some of you have actually done it, right? In Atlantic City? Or Vegas. Is Vegas. The thing that I was talking about yesterday with the 2 logs, and this actually has great applications in gambling. Greg here? Okay. I picked on him about gambling before. This just one last closing remark about this. Transactions are a huge part of the next course. The database-backed websites. Databases use transactions extensively. And you're also going to have a database course itself, and they're probably going to go through a lot of flavors. So if you have any questions about this, please ask me about them, and I can either, if I don't know the answer, I can guide you to some place where the answer is, or I can give you some ideas about how you might think about transactions in different types of databases. Any questions? Great, thank you.